with piecewise defined functions, there in your textbook, in section 3.4, there is a, I want to think it's page 245 to 249, something like that. There's a list, it's not just not like a list, but it's a definition of all the function types that we deal with here. And you can go through those and get that information about it. I think most of it's stuff you've seen before. The things on the function types that you need to know is know what the graph looks like, the domain, range, and intercepts. A lot of things we talked about already. And then increasing, decreasing. It gives you all of this information. And it's basically just learning the basics of each type of function. In that we exclude, so don't worry about the int functions. It's either written int with an x in parentheses. Sometimes you'll see this symbol. It's like a square bracket with another line in it. That's a greatest integer function. We're exclude that. You don't have to do that one. The rest of them are going to be things that come up as we do that. But you're going to see as we're doing these piecewise functions, we'll have a piece of each one of these. It's never really the whole function. It's just part of it. But that set of pages takes you through what each function looks like, just a general picture of it, being able to recognize, oh, that's a cubic, and I know that's going to help me, be able to understand certain, parts of things there. So, so go to those pages and look at those things and go from there. I may have a document that I might send you this week. I'll have to look to see if I can locate that, but that'll help you get the idea of what these parts of a piecewise defined function is. I apologize, my voice is not real great today. Good old fall allergies are on us. It's like a plague on my household. We all have allergies. So a piecewise defined function is a function that's split up into a number of pieces, and I like to think of them as parts. And part A, and then it gives you a domain for that part. And then it might have another part, and I call that part B. And then they'll tell you the domain of part B. And then some of them have a third part, some don't. It just depends on the problem. Part C, and then they tell you the domain for part C. The whole function has a domain, but each individual part has a portion of that domain. The whole function, the domain for the entire function, is based on the entire, all three parts together, but each part has its own domain. So it tells you where that's going to happen at. And with those parts, let's just take our first example here. F of x is equal to 3x plus 2 when x is less than -2. 6 when x is between -2 and 4. Equal to, mark on both of those. And then -2x when x is greater than 4. Excuse me. With these, there's some important things that happen here. Each piece has an important point or important points that go along with it. So what you want to do is you look over here in the domain area, and that's going to tell you the x values that are important for that particular piece. This one, the x value, that one of the x values that's important for it is -2 for x. So what you want to do is find what I like to call just the important points for each part. Okay, so for the first part, part A, -2 as the x value would be an important point. So if I plug that in as x, -2 plugged in as x right here would be 3 times -2 is -6, plus 2 is -4. That's an important point for that part of the graph. Okay, and I'm going to graph as I go here. So I'm going to swap over here to a piece of graph paper. If you want to graph like on a separate sheet, that is absolutely fine. I tend to do that a lot if I'm working on paper, but since I'm working on the digital paper here, I'll just draw it here. So I'm going to draw myself a coordinate plane and graph this piecewise defined function on it. Make that black. So there's a y-axis, and then I'm going to put an x-axis here, just where I know it. There we go. All right. So we got a coordinate plane. Now that first part, you have -2, -4 as an important point. So I'm going to go to that place on the coordinate plane. I'm going to -2, -4, and that would be left 2, down 4. And I'm going to put an open circle for that piece because it's an open circle because that doesn't have an equal to mark on the inequality up there. That inequality is less than only. So -2, -4, 3, 4 is going to be an open circle. And then it says it looks like 3x plus 2 everywhere that x is less than -2. So I can either follow the slope of 3x plus 2 because I know that slope intercept form, or I can just pick x values that would fit that inequality that are less than -2 and plug them in and get some points out of there. Either way, it gets you the same picture. Okay, so if I pick an x value of -3, that's less than -2. I plug that in -3, plug in for x up here would be -9 plus 2, which is -7. So I could go to -3, -7, and put a dot. That also has a slope of 3. If I go down 3, left 1, it's the same thing. And that's a straight line that connects those dots. So that's what I want to draw there. That will get me the first piece of my piecewise defined function drawn. If I picked another x value of like maybe -4 and plugged it in, I would end up right there. I could find those ordered pairs by either plugging in x values that fit or following the slope of that one, but since it's a y equals mx b. So that's the first piece. The second piece, part B, it has 2 x values that are important, -2 and +4. So it has 2 ordered pairs that are important. One of them is at -2, and then the equation says that y equals 6 no matter what, because there's no x to plug into, right? So no matter what these x values are here, y is going to be 6. So the ordered pair is going to be -2, +6. And then the other ordered pair would be 4, +6. And that's the important points for this part, the B part, because of the inequality there, the 2 ends of it. So I would want to go and put either open circles or dots at those spots. So I'm going to go to -2, 6, which would be 1, 2, 3, 4, 5, 6, right there. And I'm going to put a filled in dot. Why is this one filled in and the other one wasn't? It's got an equal to mark. It's the only reason. Okay, so I'm going to go to 4, 6 and do the same thing. It's got a filled in dot because it's got an equal to mark on it as well. All right, and then that's just a horizontal line connecting those two. So here we see we've got one part A here. Here's part B's graph. We need to get part C's graph out of that. So we need to import a point for that one. So it's going to be at x value of 4, because that's what's in our inequality. So 4 plugged in there would be -8. -2 times 4 is -8. And so I'm going to go to that point. 4, -8. 1, 2, 3, 4, 5, 6, 7, 8. And that's going to be an open circle because it doesn't have an equal to mark. And then I can either pick x values that are greater than 4, because that's what the inequality says, or I can follow the slope of -2. If I follow the slope of -2, you go down 2 and over 1, like that. Do that a couple times. If you plug in 5 for x, you get -10. Plug in 6 for x, you get -12. You get the same picture no matter which way you do that. So, I have folks every year that do it different. Some do it by knowing that it's a line and it goes that direction with the slope. Some do it by plugging in x's. It works the same either way. Here we have graphed the piecewise defined function, and we got a picture of what it looks like. Now, what we want to do is talk about the domain of the entire function. Well, when I look at the domain of the entire function, they're always in order from left to right when they put them in the function there. So the leftmost x's are always at the top. So when I look at x is less than -2, that's going, this piece, and it's continuing to go down that way, right? So the x values are starting at -infinity, and they're getting up to -2 with the first piece. But then it says, oh, don't use -2 for this piece. Go to the next piece. We go to the next piece, and it says, oh, it's got equal to mark. So that says, oh, you're going to use -2 for this guy. Okay? So because that's got an equal to mark, that means we're not skipping -2. We're just jumping to a different spot. Remember, domain is x values, and it's left and right. So here we're using the -2, and we're riding along this line until we get to 4. And it says, okay, use the 4 for the second part, but then for the third part, jump from 4, 6 to 4, -8. And if we jump down there, it's got an open circle. So we've used 4 here, but we didn't use it here. So we actually have used it. We didn't skip it. So our domain picks back up here and keeps going forever down and to the right. So that would get us to positive infinity for the domain of that. You can get the domain from the inequalities that are beside there, or you can kind of read the graph as you go. It really is up to you how you do that. I like the graph myself, but it's again, it can be done either way. The range, you really need the graph to get the range. The range is very difficult to get without the graph. So having the graph is important for that. So when we look at the range is read from bottom to top. So we read from the bottom. Both of these have arrows that are pointing down, and that means they continue forever in that direction. So that means that this one, the range is going to start at -infinity, and then it goes up on the blue one, it goes up to here and stops. But this one, the first one, is still going, and it gets up to here and stops. So that y value there is -4. We've got an open circle on it. So that means we're going to go from -infinity up to -4, and we're going to stop and skip -4. And then we're going to go over here, and we're going to pick up the next y values that get used are these up here. What y values are all of those? Every one of those on that line are the same y value. What y value is that? 6. So we're going to pick up at 6, and that's the only thing we're going to use. We're going to put a bracket around that because we're using 6 the whole way. We're skipping all of these numbers in between on the y. So that's why there's nothing else in there, because we're skipping all the other numbers. The graph is really important for being able to find the range, I think. anyway. You can do it without it, but I think it's much easier if you've got the graph. Another thing that we look at here would be intercepts. The graph is useful in helping you find those intercepts. If you can see them, what kind of intercepts can we have? X and Y intercepts. So if we look for X intercepts, we're looking for where it crosses the X-axis. Is there anywhere that this graph is crossing X? So we don't have any X intercepts. Where's it crossing the Y-axis? At 6. So we have a Y-intercept at 0, 6. That's the only intercept we have. Okay? Now, what part of the domain of the piecewise defined function was 0, 6 from? Part A, part B, or part C? Part B is where it was from. Okay, so the line, it doesn't always come from part B, but it's useful sometimes to know what part it came from out of that so that you can kind of get somewhere there. And then the last thing that we talk about is the continuity. C-O-N-T-I-N-U-I-T-Y. Continuity. Continuity talks about being continuous or not. Continuous means it never jumps or skips or has an issue where you can't trace it without picking up your pencil. So that's the best way for me to explain continuity. Is if I start on the leftmost point of the graph and start tracing it, if I ever have to pick up my pencil, then it's discontinuous. So I have to pick up my pencil to get from here to the next place, right? So that would be a discontinuous graph. A continuous graph, I would be able to trace and never pick up my pencil. I don't have to jump from one piece to another. So continuous and discontinuous are only answers that you can have there. This one would be a discontinuous. I want to show you how to graph these with your calculator. You don't have to draw a ton of graphs out of that. So I think it's helpful to be able to do a lot of these graphs with the calculator, just because it can, a lot of times the answer you're looking for is the graph. And so if you can get the pieces graphed there, it's easy to do. So on the graphing calculator, everybody's there. So I'm just on the regular calculator screen right now. I'm going to hit the Y equals button. And I'm going to clear out anything else I've got. I want to make sure if you hit Y equals on your calculator and one of these is darkened in, it'll look like this. I'll show you. If you hit Y equals and you got one of those darkened in, you need to go turn that off. To do that, you press the up arrow, get whichever one's darkened in, hit enter, and it'll turn it off because it causes issues when you go to graph. Okay? So what we're going to do is we're going to graph each part as one of the Y equals. So we got 3 parts. So we're going to use Y 1, 2, and 3. Okay, so part 1, or the first part, was 3x plus 2 when x is less than -2. So the way you can do piecewise is use parentheses. Parentheses, and then type in the first equation, 3x plus 2. Close the parentheses. And then you open up another set of parentheses, and this is where you're going to put your inequality. Okay? The inequality is x is less than -2. So I'm going to type x, and then to get the less than symbol, I hit math. Excuse me. I hit second math. Let me get back to Y equals, back where I was. All right, so I'm here. I put in the x. I hit second math, and then there's my inequality options. Okay? See all of the inequality symbols here. We need a less than, which is number 5. And then the number was -2. I want to show you what that looks like, just that one piece. If I hit graph, I see just that one piece that we drew here. It puts a blank line here because it's saying, hey, you're not using these at all. That's what it's doing. Okay, so here's that little piece that we drew earlier by hand. Y2, we're going to put the other one. It's a little bit more difficult because it's got two inequalities mixed into one, and we've got to split it apart. So when you look at this second inequality, let's right on another page here. -2 is less than or equal to x is less than or equal to 4. If you take it one piece at a time, -2 is less than or equal to x, and x is less than or equal to 4. That's what that says. Because it's just splitting it down the middle. It's like that's what that says. Okay? So we need these two inequalities in there when we go to do that part. So we're going to go to y equals on the calculator. I'm going to y2. I'm going to put a parentheses. I'm putting 6 in there and another set of parentheses. And this is where I've got to do that weird thing with the inequality. So I'm going to type, just like I've got it written here, I'm going to try it that way. -2, then second math is less than or equal to, so that'd be number 6, x. Now I need the word and you've got to go second math, go over to logic to get the and. Okay, and then do x second math less than or equal to 6, 4. Let's close the parentheses and see if that'll graph for us. We may have to turn this guy around. I'm not sure, depending on the. Oh, we did. It worked out great. So here we have part A. Here's that part B. Same picture we drew by hand, but it's nice to get that. My calculator's not graphing that. All right, let's see what's I think what it was zoomed out so far that you couldn't even, it wouldn't make it enough there to see. So now you got it. All right. Y'all good? All right. Let's get that third part. So parentheses, -2x, close the parentheses, and then another set of parentheses. I need x is greater than 4. So x, second math, option 3, greater than 4, and then hit graph. And there I see that little piece that was going to be the same picture we drew by hand. Graphing them by hand, I'm probably better at that and quicker, just because I've done a lot more of it than I am with the calculator. But sometimes if the function is got a lot of maybe complicated parts, this one's straight lines. But if one had some curves in there, it might be useful to be able to graph it with the calculator. So I wanted to touch base with that with you so that you could do that. Let's look at one that maybe does have a little bit more involved thing going on with it. So example B, let's say we had g of x is equal to this piecewise function, x squared when x is less than 2, and then -3x plus 5 when x is greater than or equal to 2. So only 2 parts for this one. But the first part's a little bit more complicated than it was before. So again, the first thing that I want to do is find those important points. And they're going to be where x is 2 for the first one. If I plug that into this equation, 2 squared is 4. So 2, 4 is where that's going to be. And if I graph that by hand, that would be nice. We'll see some things that make this a little special. And then we'll graph it with the calculator too, just to set practice. So I'm going to go to 2, 4, 2, 4, and I'm going to put an open circle. Why did I put an open circle? Not an equal to mark. All right. What do we know about x squared? What kind of shape is that? It's curved. That's right. It's got this kind of U-ish looking shape to it, called a parabola. So we can get the shape of that by picking some x values that are less than 2 and plugging them in. If I pick 1, 1 squared is 1, so I get a point there. 0 is 0. -1 is +1. 2 would be 4. If I did -3, that'd be +9. 1, 2, 4, 5, 6, 7, 8, 9. So we get this shape happening here. That's generally what's going on. That's probably not perfect, but it's pretty good. All right, so the next thing would be find the important point for part B, which would be also the x value of 2. So plug in a 2, that'd be -6 plus 5 is -1. So I'm going to go to 2, -1, and put open or filled in circle. Filled in because it's got an equal to mark. And then I've got the options of either picking x values that are bigger than 2 from this inequality or following the slope. If I follow the slope, then I'm going to go down 3 and right 1 just because I know it's a slope-intercept form equation. And get that. If I pick x values of 3 and 4, I get those same points. So it doesn't matter which way you do that. If you want to pick x values, that's fine. If you want to follow the slope, if it's a linear equation, that's fine too. So then I'm going to draw the line. Off kilter there. That's a pretty good line. Now, same story. We're going to find the domain out of that. This one, are there any x values that aren't picked up? Look here at all the x's that are less than 2, and then the other one picks up the 2. It says, okay, start using 2 and go above that. So this one doesn't have any holes in it, as far as x's that are getting left out. So the domain for this one is from -infinity to +infinity. The range, again, is going to be read from bottom to top. So we read from bottom to top. The blue one going down that way, so that's going to be -infinity that it starts at. It goes up to this y value right here, which is -1. And it uses it, so I'm going to put a bracket on it. And then what's the first y value that gets used on the part A? Reading it bottom to top. That one right there, isn't it? That's the lowest one on this part. And what's that y value? 0. So it starts back up at 0 and goes to +infinity there. This side stops, but the left side keeps going up. So we can go with the one that does the most. Okay. So there's our range based on the graph of that. Are there any intercepts to this one? Does it cross the x or y axis? Yeah, origin happens to be x and y intercept at the same time. So there's 0, 0 is an intercept for this one. Is it continuous or discontinuous? Discontinuous because you got to pick up your pencil to trace it. All right. If we wanted to graph that with the calculator, we could. We go to y equals. To get rid of something that's already there, you can just hit clear and it'll delete it completely. If you type over the top of it, it'll override it, whatever's in there. So if you wanted to overwrite, you could. I'm a delete person, so do x squared in parentheses, x is less than 2, so x second math less than is number 5, 2. And then go to the other one, parentheses, -3, x plus 5, close parentheses, x second math is greater than or equal to, which is number 4, 2, close parentheses and graph. There we see, here's the first part, same picture we got. I'm drawing it by hand out of that. So nothing, doesn't get any, much, it's same steps over and over. It's all the same there with the piecewise defined functions. Nothing just very strenuous about those. I don't know what it is about that cable, but when I touch it, it does that. Then you're done. It's weird. And then it does that. Okay. So you can see that see, this is supposed to be red, like bright red. I don't know if it's the projector or the cable that's causing it. It's okay. Anyway, all right. So piecewise defined functions, it's that process over and over. It's nothing different ever with piecewise defined functions. Look at the pieces they give you one at a time and work with it from there. So for that section, I think it's page 248 in your textbook, 9 through 49. If you look at those odd ones there, that should give you a good idea on the piecewise defined functions as to what you're expected to know out of that, and then we'll go from there. All right, let's look at 3.5, which is, I think, an easier section than 3.4 was. 3.4 wasn't terrible, but 3.5 is, I think, infinitely easier. It's about translations like King James and NIV and it's a bad joke. Sorry. Transformations. So it's basically another name for this. They used to call this graphing techniques. And the idea, and I'm not sure exactly at this point in technological lives of students, you guys have a graphing calculator in hand. So a lot of times if you get an equation, they want to know something about it, you just type it in there and let it graph it, which is absolutely a great thing. You got a great tool in your hand for doing that. But there are some techniques that we can talk about that can help you shortcut what's happening to a graph based on just some things that you see in the equation where you don't even have to type it in to know that it's shifted the x squared graph up 4 units and to the right 6. You can look at it and tell. So what's going to happen is you're going to have a y equals f of x. And what the f of x there is what's called the parent function. As in, it's the original, not a part of or a copy of, it's the original thing, okay? And you're going to shift that by doing certain things. And the one thing that is helpful to know is that vertical and horizontal movements are what we're talking about. Vertical movements happen on the outside. That'll help you remember this. Horizontal movements happen on the inside. Okay? Vertical movements happen on the outside. Horizontal movements happen on the inside. And as we go through these, you're going to see what I'm talking about as we talk about the general case. Okay? So let's take a vertical shift. A vertical shift is taking a graph and just picking it up. So like if we took the parabola, that U-shaped graph, a vertical shift is just taking it and is moving it up a certain number of units or moving it down a certain number of units. That's a vertical shift. If you take an absolute value graph, that's a V shape. A vertical shift is just picking it up and moving it so many units up or so many units down. So a vertical shift is moving that thing up or down a certain number of units. The way it works, no matter what function you're dealing with, whatever the parent function is, parent function is f of x. That could be x squared. It could be the absolute value of x. It could be x cubed. Any of the graphs that are on that in that first section that we talked about, the pages that you could look at, and you're taking something and adding it on the outside. And throughout this, k is a number. Okay, so a vertical shift, f of x is equal, or f of x plus k means you're shifting it up or down k units. An example would be if you had y equals x squared plus 2. That plus 2 is a shift up 2 units. If it's y equals x squared minus 5, what's minus 5 do? If plus 2 goes up 2 units, minus 5 would go down 5 units, yeah. Okay. And the idea of that, if we go to the graph, and is to take, I'm going to put the parent function is going to be the blue one. So if I'm going to do x squared, it normally looks like that. If we did x squared plus 2 as the red one, x squared plus 2, you see it's taking this blue and it just picked it up and moved it up 2 units. That's what's happening there. And could you get that with the graphic calculator? Absolutely. Absolutely, but it takes a little more time to do that sometimes. So if you can just recognize it by looking at the equation, it can speed you up. And all that, I guess that's one of the reasons that we still do this in college algebra at this point, is so that you can just glance at an equation and be able to tell what it's doing without having to type it in and graph it and all that stuff. And I don't know. There's different debates about this, about whether it's even needed or not. I like doing it because I think it's neat to be able to do things without having to rely on the calculator to tell you what's going on. If we take a horizontal shift, okay, a horizontal shift happens on the inside. So what that does is you have x plus k on the inside. That's going to move left. And if you have x minus k on the inside, that's going to move right. Okay, it's the opposite on the inside. If it's a plus, you're going to go left. If it's a minus, you're going to go right. It's kind of weird like that. Examples would be if you had y equals parentheses x plus 2 squared, that's going to be to the left 2 units. If you had x minus 3 squared, that's right 3 units. And again, you could go to the graph and get the same answer to that. So like, we got the parent function is still x squared, but if I do parentheses x plus 2 squared, we should see that moving to the left 2 units, right? And then if I did, instead of plus 2, I did a minus 3 in there, you should see that show up 3 units to the right out of that. Okay, so vertical happens on the outside, horizontal is going to happen on the inside, and you're going to think parentheses are going to be involved if it's a horizontal movement out of that. So that's going to be helpful. Okay, so that's shifting left, right, up, or down. Let's talk about stretching and compressing. So same idea though. Again, vertical happens on the outside, horizontal on the inside. So a vertical stretch. Did y'all guys might be too young. Did you ever play with silly putty growing up? Like the stuff that comes in a little egg thing, and you could take it and you could smash it out and everything, and then you'd get we always got the newspaper on Sunday, and you'd have like a cartoon in there like that one, and you take that silly putty and you mash it down on there, and you pull it off, the ink would come off on the silly putty, and you could take that, and I always liked Garfield for Calvin and Hobbes, and I would take that picture, and if you did this, it would stretch it out, right? And what would happen to the characters when you stretched it like that? They would look like they're getting skinnier, right? So when you do a vertical stretch, that's what it's going to look like. It's looking like the graph is getting skinnier. That's what a vertical stretch does. And the way the equation looks is you take the original parent function and you multiply by something on the outside. We're just calling it A. and A has got to be greater than 1. Because if you're going to stretch something, you're going to make it taller. So if you're going to multiply by something to make it bigger or taller, it's going to have to be a number bigger than 1, right? Can't be a fraction. If you multiply something by a half, it gets smaller, cuts it in half, right? So a vertical stretch is multiplying by something bigger than 1 on the outside. For example, y equals 3x squared. I'm using the x squared graph like crazy first here. So if I go back to my parent function is the first one, and I'm going to say 3x squared. There's the parent. Look at the 3x squared. It looks like it got skinnier. That's what it looks like, okay? So a multiplied by something bigger than 1 is a vertical stretch, but it's got to be on the outside, okay? A vertical compression was kind of the opposite. You took that silly putty and had Garfield on it, and instead of stretching it out, you took it, and if you kind of easily squished it down, it would make them get a little wider out of that. I think that's what happened to me. But you got a number multiplied on the outside. The difference is that number is between 0 and 1. A small fraction. Example of that would be something like 1/3 x squared. So example, y equals 1/3 x squared. If I look at that graph, instead of 3x, I'm going to put a 1/3 in the front. Hit graph. There's the original. The 1/3 looks like the graph got wider. It widened it out. So that's like a compression. So a vertical compression is multiplying by something on the outside. What size the number is just tells you whether it's a stretch or a compression. Big number, stretch. Small number, compression. Small number is in less than 1. Okay. All right. Talk about a horizontal stretch and compression. Kind of put it all together here. Horizontal. Horizontal stretch. Y equals the original function, but you're going to multiply on the inside by something, and that inside is going to have to be a number. If it's going to be a horizontal stretch is taking the silly putty and pulling it this way, right? That's what a horizontal stretch would be. So it's got to be between 0 and 1. Seems weird. So example, y equals, and let's do 1/2 x squared like that. Y equals, and I'm going to go over here. I'm going to use parentheses here. So I got to do parentheses 1/2 x close parentheses squared. So there's the parent, and there is a horizontal stretch. It looks very similar to a vertical compression as far as when you look at the graph on the calculator. And that's one of the reasons that knowing these rules to know what's happening, because the graph on the calculator, that looks almost exactly like the one we just did with that was a vertical compression. But the difference is the equation and what it looked like. So if you're multiplying on the inside, it's horizontal stretch or compression. Stretch if it's a small number, compression if it's a big number. Okay, so horizontal compression taking on the inside, multiplying by something, but that something is a number bigger than 1. So an example of that would be y equals parentheses, 2x and then squared. So a horizontal compression, you're going to push it in from the side, so that's going to make the graph look like what? It's going to look skinnier, right? It's going to look a lot like the vertical stretch did. So again, the picture on the graph looks similar, but the equations are much different. Okay, so when I look at that one, you got the original graph, and then I'm going to do parentheses 2x close parentheses squared. When I look at that, there's the original. The red one there slims it up because it's a horizontal compression. It's pushing the x's in as it goes there. So horizontal stretch, you got to have a small fraction in front on the inside. Horizontal compression, you got to have a bigger number on the inside. It's the opposite of the vertical. Vertical is the other way around. Vertical, you're going to have a bigger number on the outside for a stretch, a smaller number for a compression. So it's always the opposite there. All right, one more, or actually two more. They're not the same. Reflections are the last thing that we talk about here, and then we'll get into a few examples where we're trying to write an equation that does a certain transformation. So a reflection in math, when you reflect something, you're taking it and you're flipping it across an axis. So if we're going to flip across the x-axis, let's look at a little sketch here. So I'm just drawing a little coordinate plane, and I've got, if I take this little red flag and I'm going to flip that across the x-axis, where's it going to land? If I flip it across the x-axis, it does what? Boom, does that. What changes about the ordered pairs of each point on there? So this point, what changes from positive to negative? The x values or the y values? The y values. So that's a y change. Y is vertical, right? So that's going to happen on the outside. So a reflection across the x-axis is going to look like this. You're just going to have a negative sign on the outside. Example would be if you had y is equal to negative x squared. Again, we could go to our equation. The parent function is there first. Put a negative and then x squared. Boom. It just flipped it down just like that. Changes the y values sign. That's what a reflection across the x-axis does. Okay? So a reflection across the y-axis would take that same picture, instead of flipping it down, would flip it where? You would start here and cross the y-axis means jump across the y-axis. That goes over here. What changes about those? The x values change. That's right. The x values change. So that equation on a reflection across the y-axis, you're going to have y equals, and then you're going to put the negative on the inside. Now, the x squared graph is a horrible example for this, so I'm going to have to change functions. X squared, if you flip it across the y-axis, it doesn't do anything. It looks exactly the same. So I'm going to have to swap functions. I'm going to swap to the x cubed graph. So x cubed, if that's the parent, and I do a negative on the inside, like that, so I'm going to go to my calculator and show you that. So here I've got x raised to the third power. So I'm going to clear that one out. X raised to the third. And then I'm going to clear this one. So here's the original function. That's the parent. And then I'm going to do the horizontal or the reflection across the y-axis. So that would be parentheses negative x parentheses raised to the third. So to get that exponent, it's that little caret symbol on the right. And then I hit graph. Notice how it flipped it across there. So the x squared one, you wouldn't even be able to tell because it looks the same both ways. So it flips it across the y-axis. The negative on the inside does. Outside, across the x-axis, because that's a vertical movement. Inside is a horizontal movement, so that's left to right, flipping out of that. All right, so that's all of the different translations or transformations that exist that we're going to talk about in college algebra anyway. So let's look at taking a parent function and writing the equation that would happen if it did a certain transformation. Okay, so let's start. Let's just do a couple of those. So here's our function. F of x is equal to x squared. That's the parent. Okay, this is our parent function. Okay, we're going to do several examples with this, just that one. Okay, if we wanted that to shift down 8 units, what would the equation be? Yeah, x squared minus 8. Good job. And that would show us that x squared is moving down 8 units. Really easy thing there. All right, let's do shift left 7 and up 4. So do 2 at once. So we got a horizontal shift going on, so we know there's got to be some parentheses. And it's going left 7. So is that going to be a plus 7 or a minus 7 on the inside? Positive. Yeah, plus. That's right. And then the up 4 would be what on the outside? Plus 4. Okay. Not too bad. It's actually, pretty easy here. Let's say we had a vertical stretch by a factor of 6 and shift right 3 units. So a vertical stretch is going to happen on the inside or outside? Outside, because it's vertical. All right. So we know the 6 is going to be on the outside. We got some left and right stuff going on, so we know that's horizontal. So that's going to be parentheses. And how do we move it to the right 3 units? Think about what we did on number 2. Left had the plus sign, so minus will have be the right way. Go to the right. I'll be honest, the way I've remembered that since I was a kid was the I and right and the I and minus. I don't know if that's just the way I remembered it way back then, and I still remember it that way. Yeah. I guess when I was in high school when we were doing this, I didn't understand it, and so I was hunting for a way to hang on to it. I got a little better understanding of it now, so I hope I do anyway. I'm teaching it. All right, let's do a horizontal compression by a factor of 3 and shift down 11. Again, we're taking the x squared graph and doing that with it. What's a horizontal compression going to do for us? That's the hard part. I think the down 11 we can all get, but the horizontal compression by a factor of 3. In the parentheses, that's right. So is it 3x then squared to get a horizontal compression, and then the down 11 units would be minus 11. If it were up 11 units, it'd be plus 11, that idea. Okay, horizontal compression, we're multiplying by a big number on the inside. Horizontal stretch, we're multiplying by what kind of number on the inside? Small fraction, between 0 and 1. Okay, so that's how that's got to work. Last one for this example, and then we'll go the other direction where we take an equation and try to tell what happened to it. What did it do? So this last one, let's do a reflection across the x-axis and then down 4 units. So the down 4 units is going to be a vertical movement, right? So we know that's happening on the outside. So I know I got a -4. What's happening to the x squared to reflect across the x-axis? Where? Inside or outside? Why? You're right. All right, so reflecting across the x-axis, x-axis is here. If you're going to reflect across it, you're going to move like that. That's a vertical movement. If it's reflecting across the y-axis is up and down, you're going across. So that's a horizontal movement. That's the way it helps you remember, if I'm moving vertically across the x-axis is vertically. So that's going to be on the outside. So it'd be a negative and then x squared. If it was a reflection across the y-axis, the difference would be you would put that in parentheses. That's the difference in those. Across the x-axis, negative on the outside. All right. All right, let's go the other direction. I'm going to give you the original function, the parent function. So parent function is f of x is equal to the square root of x, just a different function out of that. So it's easy to determine the inside and outside of that. And let's describe the transformation. All right, so first one, say we had y equals the square root of x plus 3 and then a -6 on the outside. What would that do to the parent function? It doesn't matter what order you say that in on this one. So what does the plus 3 on the inside do? Good job. What's the -6 on the outside do? Good job. So the plus 3 is going to, I'm going to highlight here to help us tie that together. The plus 3 is the left 3. The -6 is your down 6. And I highlighted that. You can't see it at all. Let me back up and do a different color. All right. Yeah. You still can't. It's the same color. It's green on my screen. Anyway, so let's circle it then. That is that. That's where that's coming from. Okay. So you can tie those things together there. Number 2. Let's do f of x or y. It doesn't matter. I'll do f of x just to change that. -3 on the outside, and then then the square root of x minus 5. Well, since it's in the front, what's it doing to the square root? It's multiplying, right? So anytime you're multiplying by something, you're not shifting left or up or down. It does do something. The negative reflects it across what? Yep. Reflect across x-axis. So that's just the negative part. That's what does that. What does the 3 do? Multiplying by a big number on the outside. It's on the outside, so we know it's what? Vertical or horizontal? It's got to be vertical, and it's a big number. So when you multiply something by a bigger number, it's going to stretch it, right? It's going to make it bigger, make it taller. So that's going to be a vertical stretch. And then the -5 on the inside, what's it do? It goes right 5. Good job. Recognizing what each piece does there. It's all one thing, but it's good to know what each individual pieces do. Let's do another one here. Let's say we had y equals the square root, and let's do -x plus 7, and then -16. There are 3 things that are happening here. Yeah, so far. So left 7, down 16. That's right. There's one more thing happening. Very good. Reflect across the y-axis. So that negative sign right there is the reflection across the y-axis. The +7 is the left 7. The -16 is the down 16. That's where those pieces are coming from. And I'm not going to ask you which, to do that kind of diagram or anything for quizzes or tests or anything, but knowing where each piece comes from is the key, and being able to tell what all happened to that graph. Okay. All right. One more thing. We're out of here. Taking a single point and applying a transformation to it. Okay. This is the last thing we're doing here. This one is the one that some people have a little trouble with. Some people catch it the first time and it's not a big deal. But some folks have a little issue with it. So we're going to take, if the point 2, 6 is on the graph, the graph of f of x find the new point after the transformation. So we're starting with 2, 6. We're going to have a transformation that happens. We need to find the new ordered pair. Okay. So y equals -3 f of x minus 1. Okay. So the key to this is not plugging in a number. People that mess this up want to plug in the x value and work it out into this. But you don't have an actual equation to deal with here. We don't have x squared plus 7 or something like that. We've got function notation there, and it's saying, okay, here's the transformation that's happening for that point. What transformation happened? So if you will take the approach like we did in the previous example, we were actually just trying to tell me what happened to the thing. What does subtracting 1 on the inside do? Moves it to the right 1, right? What does the minus or the -3 that's on the outside right there, what's it doing? Reflect across the x-axis. And then the 3 is a vertical stretch, right? All right. So what we're going to do is we're going to take that ordered pair and we're going to do those transformations to that ordered pair. So when you think about 2, 6, 2, 6 is up in the first quadrant. So it's a point. If we move it right 1, where's it at? 3, 6, right? And then I reflect it across the x-axis. Drops it down into the fourth quadrant. So what's it change about the ordered pair? What becomes negative? The x or the y? Remember, we were up here. We flipped it across the x-axis. The y value changed signs, right? So right now we've got 3, -6. And then we do a vertical stretch by a factor of 3. What part of 3, -6 is vertical? The 3 or the -6? Why? Because it's the y coordinate, so it's an up and down thing. So if we stretch -6 by a factor of 3, that's going to be 3 times -6, which is -18. So the new ordered pair would be 3, -18. By following these transformations that are happening. It's not plugging in an x value and working it out. It's looking at what transformations are occurring and applying them to the ordered pair. And it may help you to draw yourself a little coordinate plane and say, okay, 2, 6. That'd be right there. And then right 1 would move it over here. I'm going to use a different color. Right 1. And that's at 3, 6. And then flip it across the x-axis. And that puts you at 3, -6. And then apply that. It might help you to draw it. Just sketch it out. You don't have to draw it perfectly. Just sketch it out. It might help you out of that. Let's do another one. This is takes a little bit of visualizing, and some folks can do that well. Some are not as adept at doing that, and may not be as adept at. All right. So what transformations do we see in that equation there? Down 8, left 4. Okay. So if we take the point 2, 6 and we go down 8 and left 4, where does it put it? I know 2, 6 somewhere over here. If I go down 8, where would it be? So down 6 would put me right on the x-axis. You got to go down 8 though, so I'm going 2 more. So that would put me down here at 2, -2. Left 4. 1, 2, 3, 4. What's that ordered pair going to be? -2, -2. Perfect. Good job. The key is knowing that. The problem doesn't ask you for that, but if you don't know that, it's very difficult to move that ordered pair the right way. So you've got to get the transformations that are happening and then move that ordered pair through those transformations. And drawing it out can help you a lot on that. Don't shy away from drawing that picture. Some people can do it without drawing the picture. I think it helps to draw it out of that. Okay. So section 5, that's it. On page 258, there's a chart that you can look at that talks about some of these transformations and just gives you a little picture and a little organized, more of an organized. I think it's 258. You guys got the book in front of you, and I left mine on the desk. Is there a chart on there? Let me see. That may have the page number wrong. Maybe the old version. Yeah, that green thing, so that's on page 262, 262, sorry about that. 262. I must be, have my page numbers in the older version. 262. There's a nice little green box there. Okay. All right. That kind of organizes everything. It's everything that we wrote down, but just in one spot in the books in a little bit prettier picture. On that'd be 263 that the problems start on, or is it the next page? 264. You go through 1 through 65, just pick out a few of those. That should get you prepared for quiz and test and stuff there. So it shouldn't be too rough on you there. I'll have your quiz up. It'll probably be up tomorrow, the quizzes and the test, and they'll both be due before class next week. And we will next week I will be here closer on time because I won't have a meeting scheduled, and I didn't know I was going to have. And we'll start chapter 4 next week. And the way things look like they're falling is we'll do chapter 4 the next 2 weeks, and then chapter 5 the next 2 weeks, and then you're on fall break after that. So you'd have 2 weeks to finish up chapter 5 stuff, and then we come back and split up chapters 6 and 12 in the second half of the semester there. So you'll have a little bit of a lull and things to do there at fall break. I know that probably hurts your feelings that you have nothing much to do with the fall break.
It's like the 7th, right?
The fall break, 14th. Yeah, I think that is correct. It's just Monday and Tuesday. Well, you get the 12th, the 13th, the 14th, and the 15th. So it's a Saturday. Yeah.
So 2 quizzes and our test will be due by class time next week.
2 quizzes and tests to be due by the class time next week. Guys, I appreciate it. Y'all have a great week. Email me if you got questions. I'll see you next week. See ya.